Hey everyone, and welcome to this explainer. Today, we are going to completely flip the script on how you look at biology. We're going to stop looking at life as this soup of messy chemistry and start realizing that it is actually a highly optimized dynamic mathematical system that is actively computing its own survival. Seriously, have you ever looked at a complex forest ecosystem or even just a healing cut on your hand and wondered how it all just works? Well, today we're lifting the hood to uncover the hidden mathematical software running underneath it all.
All right, so here is our game plan for today. We're going to move through 5 key areas. First, the architecture of life. Second, self-organization and emerging order. Third, self-preservation and resisting entropy. Fourth, self-reconstruction and recomputing geometry. And finally, we'll tie it all together with the mathematical spine. So let's jump right into part 1, the architecture of life, going way beyond messy chemistry. You know, when you or I think about resilience, we usually picture something physical, right? Like a scab forming or an animal toughing out a really brutal winter. But what is actually happening under the surface? The thing is, life isn't just passively enduring. It's actively solving mathematical constraints to fight against physical loss. Every single second, biological systems are essentially crunching numbers, calculating exactly how to minimize their energy costs while maximizing their structural stability. And we see the incredible results of these computations all around us in nature, from the near-perfect multi-sided geometry of a tiny virus to the beautiful logarithmic spirals of protein folding that look wildly similar to massive galaxies, all the way down to the fractal branching of your very own lungs. Biology repeatedly, almost obsessively converges on these exact shapes. Why? Because they are mathematically perfect at saving energy. These aren't just happy accidents, they are universal optimizations. To really put this into perspective, take a look at this brilliantly simple power law scaling rule. It perfectly links an organism's energy consumption, that's the B, directly to its mass and complexity, the M. Whether you're a single microscopic bacterium or a giant multi-ton elephant, your metabolic behavior follows this exact mathematical relationship. It dictates exactly how resources get distributed through those fractal branching systems we just talked about. It's pure, elegant mathematics, completely dictating biological reality. Which brings us nicely to section 2, self-organization, or how absolute order emerges from chaos. Think about a baby developing. You might just assume it's this crazy sequence of random chemical accidents that eventually somehow finds the right shape. Actually, scratch that. Early development is driven by incredibly strict reaction-diffusion systems. You have these interacting chemicals called morphogens, and they act a bit like invisible ink. They follow strict mathematical rules to literally draw ordered complex structures right out of unstable chaos. It's the math creating the physical form. And this incredible order, it translates directly into optimal flow for the organism. Your own vascular system perfectly obeys something called Murray's Law, which mathematically dictates the exact radius of your branching blood vessels to guarantee maximum efficiency. On top of that, cellular networks use scale-free topologies. Think of it like the internet or a massive airline hub system. These mathematical networks guarantee that if one local area fails, the system instantly reroutes and bounces back. So robustness and redundancy, they're completely baked in from day one. Now let's raise the stakes a bit and move to section 3, self-preservation, and how life resists entropy. To just stay alive, living systems have to constantly fight the universe's natural pull toward disorder, which we call entropy. They pull this off by acting as dissipative structures. Think of a whirlpool in a fast-moving river. It only exists because water and energy are constantly rushing through it. Life is exactly the same way. It's sustained far from thermodynamic equilibrium, relentlessly pumping energy through its networks just to hold its shape against the current. We can see this systems-level resilience incredibly clearly when we look at cancer metabolism. Tumors demonstrate terrifying mathematical plasticity. Normally, cancer cells heavily depend on glutamine for their energy. But if you cut off that glutamine, the tumor doesn't just give up and die. No way. It dynamically reroutes its energy flux, instantly pivoting to alternative pathways like glucose or fatty acids to stay alive. The system rapidly organizes its internal math to persist no matter what you throw at it. And honestly, this perfectly explains why finding targeted cancer therapies is such a massive hurdle. We're going in trying to disrupt these pathological energy routing networks. But here's the catch. Your healthy tissues, your skeletal muscle, your immune cells, your intestines, they rely on the exact same chemical rules and substrates. So trying to inhibit the tumor is a colossal mathematical puzzle.
We're trying to break the bad network without crashing the healthy systems that are using the exact same resources.
Okay, let's stop it up even further with Section 4. Self-reconstruction, and how life actually recomputes its own geometry.
When we look at highly regenerative creatures like the amazing planarian flatworm, we've got to completely throw out our old textbook ideas about healing. The body isn't just patching a wound with some scar tissue. We have to embrace a much wilder reality. The body literally recomputes its missing geometry. It completely restores its structural integrity after a severe disruption. It doesn't patch a leak, it calculates a rebuild. So how do planarians pull off this seemingly impossible regeneration? They use incredibly special stem cells called neoblasts, and these aren't just passive biological building blocks. They act as a distributed, living repair engine. They are a mobile, totally programmable resource field, just waiting to resolve the mathematical constraints of the body after a massive injury. They are, quite literally, the living variables in the body's equation. And this whole constraint-solving process? It runs like a flawless computer program in 3 precise steps. First, proliferate, a massive, rapid resource expansion. Second, migrate, a spatial optimization process to route those new resources exactly where they need to go. And third, differentiate, assigning specific functional roles to completely reconstruct the missing tissue. That is not just biology behaving nicely. That is a complex system executing a rigid mathematical program under extreme stress. If we want to strip away the heavy scientific jargon from the partial differential equations that govern this, it boils down to something surprisingly simple, in plain English. You have C, the density of the cells. You have S, the chemical signaling gradients. You have the actual physical spreading and migration, and finally F, the biochemical instructions. Simply put, these cells move, they sense their environment, and they reorganize based on chemical fields until the physical structure completely, magically, reemerges. All right, that brings us to our final stop, Section 5, the mathematical spine, our unified framework. So here is the big unifying takeaway for everything we've talked about today. Biological systems behave like distributed mathematical fields that continuously solve for structural stability under changing constraints. Life's complexity isn't some random fluke or anomaly. It is an inevitable consequence of physical matter naturally converging toward highly adaptive states of organized complexity. From the spiral of a seashell to the stubbornness of a tumor, it is all governed by this exact same mathematical spine. And that little planarian flatworm is the ultimate proof of this mind-bending reality. Its biological software is so deeply embedded into the system that destroying the physical hardware, even decapitating the organism entirely, doesn't erase the instructions on how to rebuild it. The underlying rules for the structure remain completely intact. It's an invisible architectural blueprint, just waiting to be recomputed. So I want to leave you with this final kind of provocative thought. If the very architecture of biology is mathematically hardwired into physical law just to resist entropy, if life itself is simply an inevitable mathematical consequence of energy and matter interacting, what other complex systems are out there right now, across all scales of the universe, silently computing their own survival? Thank you so much for joining me on this explainer. I really hope you never look at biology the same way again.